All right, this is section 3.6, implicit differentiation and what we call related rates. So in this section, we're going to talk about how to deal with functions that are written in both terms x and y and not just x by itself. So a function that's written in the form y equals f of x is said to be defined explicitly, meaning that y is defined by a rule or a formula f of x in x alone. Right? That's everything we've dealt with so far. But a function can also be written implicitly, meaning that y is defined by an equation in x and y together. So in this section, we're going to figure out how to differentiate implicit functions when ordinary implicit or explicit differentiation is difficult or impossible. Okay, so it gives us an easier function to deal with. Okay, so we'll then use implicit differentiation, to find rates of change. So let's look at an example of a circle. The equation x squared plus y squared equals 25 defines a circle. While a circle is not the graph of a function, the top half by itself defines a function, as does the bottom half. So if you take the x squared plus y squared equals 25 and solve for y, so subtract your x squared and then take the square root, you end up with this equation, y equals plus or minus the square root of 25 minus x squared. But I don't just have one function there, I have two different functions. The positive square root defines the top half of the circle, where y is positive, and the negative square root defines the bottom half of the circle, where y is negative. Okay? If you have the equation x squared plus y squared equals 25, that defines both functions at the exact same time. So, if we wanted to find that slope anywhere on the circle, we could differentiate the top and the bottom functions separately. So solve for y and then take your square root. However, it's going to be easier to find both answers at once by differentiating implicitly. So that is by differentiating both sides of the equation with respect to x. So remember, however, that y is a function of x. So differentiating y squared means differentiating a function squared. So what we end up with this generalized power rule that we get to use. So I'm going to write it as I talk about it. The derivative with respect to x of y to a power becomes, same rule applies, bring your exponent down, y to the n minus 1, but we have to tack on a dy dx. Okay, we have to tack on that we're taking the derivative of a y with respect to x. And anytime we're taking the derivative of the y variable, we have to tack this on. If we don't tack it on, it's wrong. So how does this come in handy? So let's look at example 1. We're going to differentiate, I'm going to change colors here. We're going to differentiate x squared plus y squared to find dy over dx, because that's the derivative. So we're going to find dy over dx. I have x squared plus y squared equal to 25. So if I take the derivative, the derivative with respect to x of x squared, I'm going to take the derivative with respect to x of, of y squared, and the derivative with respect to x of 25. I can't just take the derivative of one side, because I have to do the same thing to both sides in any given equation. Alright, so that's what we're doing. We're taking the derivative with respect to x of each individual piece. So on the first one, when I take that derivative, I end up with 2x. And what's happening like behind the scenes would be dx over dx, which we know cancels out. So we don't need it. Then the next one, I have 2y dy over dx. That one doesn't cancel out. And then the derivative of 25 is 0. All right? Now, I have the function. I'm going to come up here so I have more room. 2x plus 2y dy over dx equals 0. And the goal now, once you take the derivative and you apply that generalized power rule, the goal now is to solve for dy over dx. I need to get this by itself, and that's going to give you your derivative. So I'm going to subtract 2x. So 2y over dy over dx equals negative 2x. Then divide by 2y. So dy over dx equals negative 2x over 2y, giving us dy over dx, that derivative is negative x over y. And you're finished. That's the derivative of the function x squared plus y squared equals 25. So the basic rules of derivatives apply. Nothing fancy there. We just have to apply dy over dx anytime you're differentiating the y. Alright? So now that we have that derivative, we can find slopes. Okay, so remember this derivative is just the slope. So we want to find the slope of the circle, x squared plus y squared equal to 25, at the points 3, 4, and 3, negative 4. Well, we already have our derivative. Dy over dx is negative x over y. So, at the point 3, 4, that gives me dy over dx gives me negative 3 over 4. So a slope of negative 3 over 4. And at 3, negative 4, that dy over dx, that slope, gives me negative 3 over negative 4. And all I'm doing is plugging in x and y, because every ordered pair is x comma y. So nothing fancy. On this one, though, negative 3 over negative 4 simplifies to 3 over 4. So we have a positive slope. And I drew the graph down here. Not super good, but I drew it. We have at 3, 4, you can see that the slope was a negative 3 over 4. You can see it is decreasing at that point. But if you look down at 3, negative 4, the slope is increasing. The slope of that tangent line. And that's it. That's finding the derivative and using that implicit differentiation to find a slope. Alright, so example 3, we're just going to find some derivatives, both implicit and explicit derivatives. So the very first one we have is the derivative with respect to x of y cubed. So when I find this derivative, I have 3y squared dy over dx. And again, since it's a y, I have to apply the dy over dx. On b, though, the derivative with respect to x of x cubed would just be 3x squared. And the biggest hint here, no matter what variable you're differentiating with respect to, if that bottom variable and the variable inside your function match, you don't have to tag anything on. But if they are different, as in part A, you have to have that extra part tagged on. Alright, let's look at part C. I have the derivative with respect to x of x cubed y to the 5th. Alright, this is going to be a product rule. Your first part is x cubed. The second function is y to the 5th. Okay? So when we take that derivative, it's the derivative of the first times the second. So I have 3x squared times y to the 5th. And since I took the derivative of an x, I don't have to add anything on. Plus the first times the derivative of the second. The second would be 5y to the 4th. And then I have to tag on my dy over dx. So if we simplify this and rewrite it a little bit, we end up with 3x squared y to the 5th plus 5x cubed y to the 4th dy over dx. And you're done. Again, on the first part of that equation, we only took the derivative with respect to x of an x, so I don't have to tack anything on. All right, so here are the rules for implicit differentiation, or the 3 steps that you need to follow. 1, differentiate both sides of the equation with respect to x, okay? And when differentiating a y, make sure and include your dy over dx. Step 2, collect all terms involving dy over dx on one side and all the other terms on the other side. Then step 3, factor out your dy over dx and solve for it by dividing. Those steps will happen every single time. All right, I'm going to stop this video here and we'll start with the next video on the next example.